recording is rolling again. Right, so I did see you guys grade your procedures. You guys have been getting good scores. Remember, score yourself out of 12. Remember, I'm not counting off if you don't get a good score out of 12. I don't really care about that. What I do care about, what I'm actually grading you for is, do you have your data? Do you have graphs? And do you have your procedure written up? Okay, so if you got like 5 out of 12 or something, then in that color, with that color pencil, I guess, write 5 out of 12 and circle that. And that's not going to ding your class grade. That's just for your own reference. Okay, well, that's how I did in the first one. And this is our first run through too. So as we do future labs, like, okay, I remember how the last one worked out, and then you'll get better and better things. Okay. And so we'll switch over to Excel. I'm gonna get some of you guys to volunteer your data. So switch my screen, present screen 2. All right, I think we're good. This over here. All right, so first one is mass versus time. Does anybody want to volunteer their data for that one? Here's time. All right, how about Stuti? What were your different, let's go different mass values. What were your mass values? 31.89 grams.
And then 81.9.
All right.
131.89. 1.89. And then 1,031.
Ooh, all right. Got a whole kilogram on there. All right. Let's see. If you want more, where's my, here we go. All right, if you want more decimal places, there we go. All right, and what were the corresponding times?
So time was 3.6. And then 3.51. 5.0. 3.40. 3.76. And 3.62.
All right. So looks like we got one outlier, but aside from aside from this outlier, see how regardless of the mass, whether mass was tiny or like over a kilogram, it took about 4 seconds regardless, right? Okay. So let me do this. I'm gonna right click on one of these. Oh yeah. Oh, that was supposed to be 3.76. Oops. All right, sorry, I typed it wrong. All right. Oh yeah, that looks even better. All right. Yeah, tell you what, everybody else, you're also at least get the shape of this graph. So if you were not in this group, go ahead and whip off a pair of axes real fast, go mass versus time, throw a title on it. And the ones you actually collected data on, I hope you guys have labeled and scale axes. So like if you did this one, you could be like mass in grams versus time in seconds. Okay. But if you did not have this one, at least get the shape of the graph down so that you can reference it later. You look back and say, oh yeah, that is how that lab worked out. I'm going to right click on one of these points, go to add trend line, and okay, that is not what that should look like. Well, okay, we're going to kind of ignore that trend line because that doesn't really make any sense. Get rid of that. Control Z that out of there. Okay. You guys see how that's basically a vertical line? You guys do see that, right? Okay. Well, you have like 30 grams over 1,000 grams. It takes 4 seconds regardless to roll down, right? So the line of best fit is just a vertical line. Okay. And what does that mean for the line to be vertical? That means there's no relationship between those two variables. Right? You can make the car whatever mass. That's interesting. Hey, those heavier cars, do they have more gravity force pulling on them? Yeah. Right now, if you go back 500 years ago and ask people, what do you, or maybe you even hypothesized before you started building the cars, or what do you think people 500 years ago would have said which car should reach the bottom first? Yeah, most people would have said a heavier one, right? And their basis for that would have been, well, Aristotle said that 2,000 years ago, and we have logic, and they didn't have science back then. So, but then this is actually what you guys just proved here with this data is the Galileo experiment. Galileo ran to the top of Leaning Tower of Pisa, threw lots of different objects, different masses. Okay, so different masses, different weights, they all fell together. So even though the heavier ones have more gravity force acting on them, turns out they also, because they have more mass is more inertia, and those two effects exactly cancel each other out. That's a future topic, but giving you guys the explanation. But for now, you see that, okay, there's no relationship between mass and time. Right? Yeah.
Is it because of air resistance or something?
No, it's not air drag. It's like if an object is 10 times as massive, it also has 10 times the gravity force. Yeah, actually, here, this is a few weeks in the future what we're doing, but you guys see Newton's second law of motion on this poster up here. So F equals ma, or you can rearrange and get acceleration as force divided by mass. So you guys get you have 10 times the gravity force and also 10 times the mass. Those just cancel each other out. You get the same acceleration rate, right? Okay. Therefore, the same time to roll down. There you go. There you go. All right. So next one. Oh, okay. So you guys got so again, if you worked in this group, just do mass versus time. Just go like vertical line. Just say, okay, that's the general trend. It's just gonna be a vertical line. Okay. Okay. Yeah, just have the shape of the graph. But okay, that's the relationship. There's no relationship. Okay. Next one. X versus T. Who was in this group wants to volunteer their data? Let's track of which groups are which. Here. We're doing yeah, that's right. You guys in the corner. Right, so Connor, what were your different displacement values?
Got 22 points or 227,
227,
200,
200,
175,
175.
150,
Bump off a couple. All right, 150,
and then 125,
125. All right. What were the corresponding times?
3.47,
3.47,
3.37,
3.37,
3.27,
3.27,
2.87,
2.87,
and 2.73.
2.73. All right. That's about what that should look like. Okay. Right, so you guys have your graph made already? Right now, everybody else, go X versus T. Okay. Now, what relationship do you guys think that's going to be? Show a hand. Here, we'll just do like yes or no. How many guys think that's going to be a linear relationship? How many guys think yes, that looks pretty linear? Okay. How many guys think it's going to be not linear? Okay. I think most of you guys got that right. Because like at a glance, it looks kind of linear, right? But then if you extrapolate backwards, wouldn't that have like a massively negative y-intercept? Now think about what that would logically mean. You know, you might go back to the lab just to get more empirical data, but don't worry. But here, wouldn't that mean at 0 time that the car, like if you let the car go, it immediately jumps backwards before it starts rolling? Right? That doesn't really make any sense, right? That's what a negative intercept would mean. At 0 time, the car would have been in a negative position. Didn't that car start out time 0 at position 0? Right? Okay. So, right, so you got the vertical axis is x measured in centimeters. The horizontal axis is time measured in seconds. You have those labeled. Right? Then, so if there should be a point here, right, you consider that. What shape do you think this actually is if it's not linear? Yeah, you guys think that's actually a parabola? Right? Now, this will be something common that you see throughout the class for future labs too. Parabola is really common. It's like even a square root, it's like a sideways parabola, right? And if you get too far out on the tail, then at a glance, your data points might look like a linear relationship. But then think a little bit about it, or go back and get data points closer to 0. Actually, it's like a curvy relationship, probably a parabola, right? Okay. Now, suppose we might suspect a parabola. Maybe we, because how do we know it's not like a cubic relationship or a time to the fourth relationship? Might be that too, right? The kind of line up with this point, right? So suppose you suspect this is x versus t squared, some kind of parabola, right? Well, do you guys remember what we did with that circle? Like the area versus the radius was a parabola. So I had you guys graph area versus radius squared and that linearized like a straight line. So that's the next one we're about to do. Right. So if you didn't have this one, did you guys do x versus t and have basically a parabola shape? X versus t is a parabola. Okay. So the next one lined up. Let's do x versus t squared. Does that look? And all I did was here, just to show you guys how it went from one to the other. So it's the same data. So x just copy pasted. See those 5 numbers, 227 down to 125. 227 down to 125. It's the same numbers. But then it just had Excel automatically square the time. So 3.47, what is that squared? See, it just takes that cell and squares it. Okay, so all the time values are squared. Graph it, x versus t squared. So the vertical axis is in centimeters, and the horizontal axis is in what unit? What's the unit on the horizontal axis?
The horizontal axis is the time.
Squared, which is like square seconds. All right, so the horizontal axis label t squared is the variable, and the unit would be square seconds, like second squared, right? Do those points line up in a straight line? They sure do. I'm going to right click one of these, go to add trend line. Where's display equation? Display equation on the chart. Look at that. Lines up really nice, doesn't it? You guys see this y equals mx plus b? Right? You guys see that? Except instead of y, it's, well, x for displacement. And instead of this x, like generic algebra x, that actually represents what again?
Oh.
Yeah, or no, sorry, the 17 is the slope, right? So the x variable represents t squared, right? So we're set, like this x and this x are different things. So this y is actually this x, and this x is actually this t squared, okay?
Okay.
So you guys see, it says x equals 17.8 times t squared. Okay. And what units are attached to this? The 17.8 number, that has units, right? What are the units that go to that number? It's not just a naked number. 17.8 what? Centimeters per second squared, right? Because if you have some seconds squared as your variable, as your x, like, independent variable, okay? And multiply that by centimeters per second squared, don't the second squared cancel out and it leaves you with centimeters? Which describes how far it rolled, right? So it's 17.8 centimeters per second squared is the slope of that line. Okay. Any questions about that? That number has units. Okay. Oh, and see that y-intercept right there? The minus 1.2, right? You guys can see visually that that's basically 0, right? I mean, that line crosses so close to the y or the origin. Yeah.
So is this the acceleration graph?
This does have something to do with acceleration.
Or is that just
Actually, I'll tell you what the connection is. So that 17.8 actually ends up representing half of the acceleration. Okay, now that's not going to make sense exactly right now, but let's see, we've got another hour in class almost. Okay, at least later this week. So sometime later this week, I'll show you guys why the 17.8 centimeters per second squared ends up representing half of the acceleration of the car. The definition of acceleration is the rate change of velocity. It's like the rate that's picking up velocity. Okay. So x versus t squared, linear relationship. Okay, you guys get that? Okay. All right. So, next one. V versus T. Okay, now this one is going to be a classic graph. Like if there's any one graph that you took extra time to like memorize for the day, there's a lot of information that's going to be embedded in this one. Okay, so who had this one wants to share their data? Yeah, go ahead, Leah. What were your different? Let's start with time. What were your different time values? 2.7 seconds.
2.06.
2.06.
2.29.
2.9.
1.96. And 1.39.
Okay. And then what were the corresponding speeds?
1.12.
1.2.
1.03.
Sorry, what's that?
1.03.
1.3. Oh, let me get some more digits on this. Let's expand this out. There we go. All right.
0.89. 0.89. And 0.76.
Okay. So I do see your horizontal axis, that's times and seconds. Then your vertical axis is going to be like speed or velocity in meters per second. Okay. And hey, it looks like the more time it's been rolling for, the more speed it's picking up. Is that? Okay. Okay. How many of you guys think this is pretty much going to be a linear relationship, direct relationship? Yeah, actually, you guys are right. so that one turns out to be a direct relationship. Okay, you do a line of best fit. I know there's only 5 points here, but if you got like 10 or 15 points, it would show even more. Yeah, it's gonna be a straight line. So if it's been, let's see if you guys are following this. If the car's been rolling for 3 times as long, should it pick up 3 times the speed? Yep, that's what a linear or a direct relationship is. There you go. So direct relationship. Okay. Okay. All right, you guys ready for the last experiment? Okay, so V versus T, linear. I remember I was gonna mention this. Let me do this. I'm gonna get line to best add trend line. Okay, that's what it should be. This actually should cross with the origin, so close enough, I guess. But let's get the equation, display equation, right? So look there, we got y equals mx plus b again, right? Oh, actually, should blow. It's gonna blow this up. That's much easier to see, isn't it? Right? So the intercept is, let's just call it about 0. So that slope right there, the 0.27, okay, what unit is attached to 0.27? That's 0.27, what? Well, how about this? If this horizontal axis is in seconds, right? And the vertical axis is in meters per second, what is rise over? Hey, shouldn't slope be rise over run? Right? What is meters per second divided by seconds? Meters per second squared. That's what that would be, right? Meters per second per passing second. Hey, if you guys are driving in your car and you're watching the speedometer needle move, wouldn't the rate that needle moves be picking up some miles per hour every passing second? And we're not going to do miles and hours in this class. We're just going to do all meters and seconds. So would it be like meters per second per passing second, which is meters per second squared? Guess it? Okay. And that also works out algebraically because you have a meters per second squared multiplied by seconds, however many seconds it's been rolling for. Doesn't that bring you up to some meters per second? Like some speed is picked up to? Guess it? Okay. Yeah. So there we go. So, and that actually is exactly the acceleration. So that value represents the acceleration. Let's compare. So say we take that 0.27 meters per second squared. Let's call it the acceleration, right? Let's compare to the other values because I told you guys before x versus t squared that this represents half the acceleration. Oh, but the units are different too. So I think it's centimeters per second squared. So meters per second squared would be like 0.18. Say if you double that, say 0.36. Oh, that actually worked out. That worked out. Okay. So I'm going back to the last one. Remember x versus t squared? I told you guys that this 17.8 value represents half of the acceleration, and I'll tell you why. Probably tomorrow we'll get to. Right? Now that's centimeters per second squared. So meters per second squared would be 0.18. Is that right? 0.18. Okay. So if you double it, that should represent the acceleration. That's like 0.36. Okay. Now you guys had different cars. They might have rolled a little bit differently, so that's not exactly controlled. But you guys all did have the same angle, and that's the reason I wanted you guys to all have the same angle, so we can kind of do some comparison. 0.36. That's extremely close to 0.27. You guys see that? So I'll kind of line up. Okay. But there's one experiment left. Right now, this one's a really weird one. I kind of debate, should I have you guys do this or not? And there's a relationship here, so this one's kind of the odd one. Who wants to share their data for this one? All right, go ahead, Rick. What were your different distances?
0.3,
0.3 meters,
0.6,
0.6, 0.9,
1.2,
5. Right. And what were your corresponding speeds?
how many decimal places?
Which guy?
We did 4.
Okay, sure. Yeah, which guy?
0.5467.
5, 4, 6. Wait, did you were using that speed sensor? You gave me that?
This is the average.
Oh, the average. Okay, yeah. I'll go ahead and let Excel round to, let's say something like that. Okay, go ahead.
0.76,
That's it.
0.94,
Wait.
1.09, and 1.21.
Oh, look at that graph. That's a really nice looking graph. Right, V versus X. Right. I should tell you guys. I know I've been calling this kind of the odd graph. You're probably not gonna maybe see this graph ever. It might pop up once. Some of those other graphs, like here, pause real fast. Like the last one, V versus T. you're gonna see this like a million times, this, the V versus T, you'll see like a million times in this class. V versus X, well, you're seeing it today, I guess. So. Okay. Hey, what relationship do you guys think that is? That looks like, just like a square root, doesn't it? Okay. Oh, now, how would you know for sure it wasn't like a cube root or fourth root? So it might be that too, right? Okay, so if you suspect a square root, which you'd be right, then hey, could you like square the V axis, the vertical axis? And then if you were correct about it being a square root, versus its other shapes, then that should linearize the graph, right? Okay. Okay, so same idea as before. Oh, you guys got V versus X on your page. You guys got a square root looking relationship. Okay. All right, so I had Excel just copy paste the distances in this next table, but also square each individual speed. And oh, look at that. Look at that. Wow. Add trend line. Okay. And before having it, let's go ahead and display equation on the chart. Right. So there's definitely a slope there. Let's think what would the units for that slope be? If you have meters squared per second squared on the vertical, and you have just plain meters on the horizontal, what is rise over run? What is meters squared per second squared divided by meters? And that's also meters per second squared, isn't it? Which is like an acceleration type unit. Right? Now, I'll tell you what, this represents double the acceleration. So to get to the acceleration, you have to take half of it. Let's see what that would be. So it says 0.98. Half of 0.98 is what, 0.49, right? Which is, that's in the ballpark of, okay, so it's kind of in the ballpark, right? It's the right order of magnitude. Okay. All right, so V squared versus X linearizes. Aha. Okay. So everybody got all the graphs? Okay.
Can you go up to the VBX?
V versus X. Okay. Okay, so just make sure everybody's on the same page here. Whatever data you actually did for your own personal lab, remember there's 4 different labs going around. Whatever you did for yours, make sure you have your axes scaled and labeled and all the points exactly where they go according to your data. And then, right, but then for the other 3 labs, just have the trends. So like label the axes and then whatever shape it should be. In this case, you're looking at a square root right there. Okay, you guys got all this? Okay. Oh, good. We have a half hour left in this class. Okay. So hang on to those lab pages for now because I'm going to give you guys. Do you guys see that green poster up there? It has 3 kinematic equations. Right. I'm going to derive those for you guys, and they will align exactly with the lab data that you guys just got. Okay. Oh, yeah. Okay. So V is on the vertical and X is on the horizontal for this one. It's always Y versus X. So V, X. Yeah. Right. So V is in meters per second, X would be in meters. Okay. Okay, you guys good there? So let me switch the screen back over. So go ahead and